This program is brought to you by Stanford University. Please visit us at stanford.edu.
This presentation is delivered by the Stanford Center for Professional Development, providing graduate-level education to working professionals, online, on campus, and on-site. For more information, please visit study.stanford.edu.
Today's speaker can be introduced the same way every time he talks. He will take the opposing view. However, he's been right often enough in opposing the conventional wisdom that people keep asking his opinion. And if you notice his list of jobs, they're all sort of manly, except for he's never been a pirate. I mean, what kind of man has never been a pirate? Today he's going to tell us... He's been a pilot, not a pirate, yes. Today he's going to tell us why the microprocessor will not dominate the future of hardware design as it has the past. Nick Tredennick.
Thank you. Wow. I guess I'm ready to get this started. I actually didn't prepare the talk till this afternoon, but I've had the slides for several years. So what I did was I took all of the slides that had just words on them and threw them out. So this is going to be completely extemporaneous. What I'm going to talk about is where I think computing is going and why. So this is a little bit of a lesson in economics as much as anything. So let's start with the economics. Here's this chart, which is probably unreadable, but it doesn't matter because I made a lot of this data up anyway. What this is doing is it's showing the world semiconductor market. So this is the worldwide market in semiconductors is the blue line that's all squiggly there. What I'm going to do later is I'm going to straighten that line out and use it in a whole bunch of charts. But what you see here, and you can see that big peak in 2000 when the dot-com market crashed, that we were doing pretty well right up until then. And now we've gone way past that already, and so we're around $250 billion a year in the semiconductor market. And it grows at a rate of about 10 to 15% per year if you smooth everything out over 5-year averages or something, and it looks like it'll keep doing that. In fact, I'm going to say that it'll keep doing that, and I'll tell you why I think it'll keep doing that. The green line on this curve, on this chart, is the gross world product. Now, the gross world product is on there in trillions of dollars instead of billions of dollars, and you can see that currently the gross world product is around 52 or 53 trillion dollars. Now what's interesting about that and why it's relevant, of course, is does anybody care about the semiconductor market? Look, the scale in these two is 1,000 apart. So the semiconductor market's inconsequential in the gross world product. It's not enough to notice yet. But there are three things that are important about this chart. First, well, I don't even remember what they are actually, but I remember one of them. First of all, you can see this gross world product is starting to move up faster. It's accelerating. We're starting to, actually what's happened is globalization, right? It used to be that the whole world economy ran on about 1/3 of the people. It ran on about 2 billion people. And in the past few years, we've had 2 billion more people kind of join the party. You know, they've started producing things, which is good for everybody, as I hope I can convince you later. So those are at least two of the things that are important here. First of all, semiconductor market is 0% of gross world product. Secondly, gross world product is starting to accelerate. And the growth rate in the semiconductor market is about twice that of the gross world product's growth rate. So what that tells you is that electronics is penetrating everything, and it's going to become significant someday, probably someday soon. All right, so here's that same curve, and I've just smoothed it out a little bit so I could kind of tell you what happens over time to the semiconductor market or in the semiconductor market. And here I've kind of got three colors that don't show up very well on here, but I've divided into the three general areas. You know, what we had in semiconductors, then what happened when the integrated circuit was invented, and then what happened in the era of computers and microprocessors. And what I put on here, again, these are just kind of my feel for what was going on. is the various products that kind of dominated the market. Now, if the market's small enough, who cares, what dominates it? But first there was a transistor radio, then the TV set, then the microwave oven, then the VCR, then the PC. And the PC was the first time it really mattered what it was that was dominating the market, because that was the time the PC at one time was about 40% of the total dollar volume in the semiconductor market. So that's truly what's called a killer application, a killer app. And so there's this constant search in the market for, what's the next killer app? What's the next killer app? And everybody thought, yeah, it's the cell phone's the next killer app after the PC. And so now you see lots of articles. If you go Google killer app in 2010 or something, you'll probably get 1 million hits, and people will be speculating about what's the killer app. And so that's when I try to answer that question, what's the next killer app? Actually, I'll answer it now. There's not going to be one. So let's do something else with this curve, which is, I'm going to throw out all that, the killer app stuff, and talk about what made the systems, what percentage of the market, what was anything that was sitting back there. So if you're back here in the transistor radio days, actually my experience goes back to the vacuum tube days, but what I'm going to do is just describe how I think the market's been developing over time, and then we'll talk about from today, where do we think it's going to go beyond, what's the next 5 years hold or something. So integrated circuit came out in 1960 roughly. Before that, everything, the whole market, everything was just built out of transistors. Once the integrated circuit was invented, then all of a sudden we got these things called TTL, little logic modules that everybody built systems out of. We got the Texas Instruments cookbook of devices, and you could build anything. It was a great time in the industry. But what TTL did was it essentially ate the market in transistors, except for some irreducible minimum in analog circuits and things like that. But it just essentially took over the market. The other thing that ate into the market was application-specific integrated circuits. So logic blocks and ASICs came about a couple years after this, 1960. I don't remember what the date was for the first quad 2-input NAND or whatever it was, probably 1963 or something. It wasn't too long before that happened. So TTL wiped out the transistor, ASICs came along, the market's growing at the same time. The next development was the microprocessor. Now there's a whole big story behind the microprocessor. I don't see any of the guys that are in the Inventors Hall of Fame for the microprocessor, so I'll go ahead and say I thought the microprocessor was actually invented in 1969 by a guy named Lee Boisel, who was at Four-Phase Systems and did something called the AL1, which appeared in a magazine article in Computer Design in April of 1970. Four-Phase Systems was shipping systems in 1969 and 70. It was actually in a terminal, but the AL1 looks to me like a microprocessor. Now what happened was Motorola bought that company. Four-Phase Systems had a whole raft of buildings out there on the corner of Stevens Creek and De Anza, not 2 blocks from where Apple is now. Motorola bought that, killed Four-Phase Systems and destroyed the company. In fact, destroyed all those buildings out there after occupying them for a while. But anyway, so that left Intel free to rewrite the history of the microprocessor. So commercial introduction of the 4004 in 1971, Intel's has successfully rewritten history on that. In any event, the market's still growing. Microprocessors essentially take over everything. What's interesting about the microprocessor is that it was a change in design methods. Before the microprocessor, everything was hardware. All your resources were in hardware. The algorithms had to be implemented in hardware. You had to be very good to conserve transistors because transistors cost a lot. So you had to really be skillful at logic design. But what the microprocessor did is it essentially made problem-solving programming. Now you didn't have to be a skilled logic designer anymore. The only guys that really had to be skilled at that were the microprocessor designers, right? They designed something for you. Then a whole bunch of standard components just proliferate in all applications. Now you have fixed hardware and variable algorithms. And so that just took over the market and grew really rapidly again. Oh, I'm backing up. Okay, so the next wedge on here is you're going to be scratching your head. What the heck is that doing on there? So I put 1983 on here as the advent of programmable logic. Well, and this is not to scale either. So on a diagram that was to scale, this FPGA line wouldn't be big enough to put the letters FPGA in there, right? It's like an inconsequential, it's like the world market versus the semiconductor market. So FPGAs don't belong there. And so this whole thing is not to scale. I've arbitrarily made it so you can read the thing. But it's important because of its place in the future. So I've put FPGAs on here. And I've put them on here in 1983. Now that's another one of those things where, gosh, the original patents were filed by some poor sap who got them in the field. You know, he got his patents issued long before it was practical to build FPGAs. About the time those patents expired, Altera started a company in 1983 and then Xilinx in 1984. And from there, the industry sort of took off. But the original patents were approximately 17 years earlier. So too bad for that guy. Anyway, FPGAs carved out a little wedge too. What did I do? Oh, I added one here. So this looks like the same chart. Well, it is the same chart, except what we care about in the future is what happens on these white spaces. You know, which way do those lines, back here, anytime in the past, you know what happened. Somebody's already analyzed the market, the sales figures are already in, it's already on paper, it's history. You know what those market shares were, right? But if you get out here and maybe today's sitting in here somewhere, there's some white space out there, and we want to know, is the microprocessor going to fill that white space, or the FPGA is going to fill that white space, or the ASIC's going to come back? What's going to happen in there? Well, it turns out as ASICs got more and more expensive, somebody said, gee, you know, I can't design an application-specific integrated circuit for a market that's not big enough. You know, because essentially every process generation, the design cost doubles. When the design cost doubles, you could say by rule of thumb anyway, at least, I mean, to a first approximation, you're going to need a market that's twice as big in order for that to be a cost-effective thing to do as a design. So think about that. We've been through, 20 generations of progress here, and we're gradually narrowing it down to where it's just not cost-effective to reach any market with a custom design from a single company. So what happens then is this thing called an application specific standard product. A company like Texas Instruments will design a baseband receiver, and they'll put some parameterization options in there so that they can sell it to 4 or 5 different original equipment manufacturers who will then customize it for their products. And so now, instead of being an application-specific integrated circuit, which belongs to one manufacturer, there'll be somebody that manufactures them to sell to a bunch of people that will put them in products. That's an application-specific standard product. That's what Texas Instruments does. That's what Garmin does. Well, maybe Garmin doesn't sell to anybody, I don't know, but the GPS receiver guys that sell chips sell them to everybody, right? And they probably have customizable parameters so that the different manufacturers can differentiate their products. And here's the same thing. ASSPs, these application-specific standard products, they've been introduced to the market now as an offshoot, essentially, of application-specific integrated circuits. What are they going to do? Are they going to take a chunk out of the ASIC market? Are they going to take a chunk out of microprocessors? You know, what happens in this wedge? Who does this piece belong to? Is this the ASSPs or is this microprocessors? So the real question is, what's going to happen in the future at these boundaries between these devices? Same thing here. Multiprocessors I'll talk about a little bit as well, about what they are and where we're going with those things. But they're sitting, I think, in this other gap. And the question is, are FPGAs going to take more market share? Are multiprocessors going to take market share? What about microprocessors? Is the single processor going to grow or shrink? So So the fluctuations on those boundaries are the things that are important to the future. And this is roughly where we are today, approximately a $250 billion semiconductor market, 2008. So if we're standing here looking that way, looking toward the things that have already happened, we already know where all the boundaries are. You know, it's interesting. You can look back and you can go, oh yeah, I know, such and such had this % of the market, and I know exactly why that was so. Because it's so much easier to look backwards, having known where you are, to say, why, yes, of course TTL wiped out the transistor. It's obvious. I mean, it raises productivity for the designer. It reduces the system size. Everything's more reliable. All those reasons, fine. Yeah, it wiped out the transistor. ASICs wiped out a segment of the market. Yes?
So where does memory sit in there independent of processors?
Actually, I don't have memory on here, so that probably would be a big bias underneath the bottom of this whole thing, because memory fits on everything. So yeah, I'm only talking about component segments, so it's missing. Memory's missing. So are all the peripheral chips, all the junk logic that's in there. That's really I saw some breakout of that stuff today. Well, I'm not going to talk about that, but it's missing. Okay, so this, I've probably seen this, well, some of you may have seen this before. This is my model of the market, and I call it the zeros model. And what it is, and it's intended to represent either the dollar volume or the unit volume of the market with a bubble of a particular size. And originally, when I did this, I divided it into 3 segments. First is the zero cost segment. That's consumer market. And so if you're designing hair dryers for some Revlon or somebody, you're a design engineer for them, then your manager is going to come to you and say, look, consumer market's highly competitive. Your design objective as an engineer doing the next generation hair dryers to get the bill of materials down to 0. And the reason you get it to 0 is because even $1 in differential cost means 15 points in the market percentage. So your design objective is 0 cost. So that's the huge market. That's everything, electric toothbrushes, transmissions, anything that's a consumer item, 0 cost. The second bubble is 0 power. So that's things that wristwatches, smoke alarms, anything that needs to be run for years on weak ambient light or body temperature or something. So again, if you're designing a smoke alarm, they're going to come to you and say, look, this is a smoke alarm. I want it to sell at Kmart or Walmart. So it's a consumer item. And secondly, it's got to last for 15 or 20 years on the ceiling, because those guys, they'll never change the battery. All right, so your design objective is 0 power. And because it's a consumer item, you're in the overlap between 0 power and 0 cost. But there are some 0 power things that don't have to be consumer items. Military probably has flashlights or something that they pay $4,000 a piece for, and they want them to last for a year or 2 without changing the batteries. And then there's 0 delay. That's a performance thing. That says from the time I ask you a question or ask a system a question until I get a response, I want to be 0 time. So you can imagine interactive games, for example, if you're a designer for game systems, then your objective is 0 delay. And if it's a commercial product, of course, it's 0 delay and 0 cost, right? Or if it's a portable consumer compute intensive item like a cell phone, it's going to be overlap of all 3 of those: 0 delay, 0 cost, and 0 power. And so I wrote a little paper on this model, and I sent it out to, there's a guy named John Wharton who used to teach EE380K for I think 50 years or so. I don't know what happened to him. He probably, well, he's still around. I'm sure he's still around. Anyway, I sent this to him, and he says, you forgot the 0 volume market. And I go, well, what's the 0 volume market? Well, there's an unassailable argument for the 0 volume market, so I had to put it on there, and that's where it is. So best example I can think of is, well, actually he thought of a great example for that, but I was thinking about it a little bit yesterday, and I thought, well, does Budweiser really need Clydesdales to deliver beer? right? No, probably not. So that's really a zero volume market, that Clydesdale market. So if you've got some other purpose than getting into the market, if your actual purpose, actually the job that I really want is I want to be a CTO somewhere because it's a high pay, do nothing job, right? Now if I were writing a job description for a CTO, what my job description for that guy would say, I want you to be in the zero volume market. I want you to get headlines. I want you to be the keynote speaker at virtually every conference. I want you to get headlines in EE Times or whatever residues left of that now. But so you need to be out in front to build image for the company. And that's a zero volume market. All right, so let's zoom in on this a little. Personal computers. Personal computers fit in this little pink wedge here because originally they're a consumer item, right? And they originally sold on performance. Everybody, I need the, what was it when they first came out? I need the 4 megahertz machine. I need the 8 megahertz and 16, 25. Now we're up at 3.5 gigahertz or something, right? They used to sell on performance. So it's a consumer market, so it's zero cost. It's a performance-oriented market, so it's zero delay. And for the whole life of the PC, the design objective for that is cost performance. Most of those things plugged into the wall, so power was kind of a free variable. Now it wasn't entirely in the laptop market. For the most part, these systems plugged into the wall, and they really worried more about cost performance than anything else. Well, let's talk about, yes?
Where is the FPGA market?
The FPGA?
FPGA. Is it zero volume or FPGA?
FPGAs? Okay, so the question is, what's the FPGA market? Where does it fit in this stuff? And it really could fit anywhere, because it's a component and not a system. And so the system's supposed to go somewhere. Now it turns out because memory is not very good for FPGAs, they don't fit very well in mobile applications, and we'll get to that a little bit, but I'm not going to answer that question because it doesn't really, they can be anywhere. Okay? All right, so now here's another thing that, PC is a commodity today. It wasn't always a commodity. It was, remember when they first came out, everybody wanted the next PC with twice the clock speed or more memory or faster, something, bigger. So, right, you're buying at the leading edge all the time. And of course, the nerd community is always sitting at the leading edge. And so what happens when the PC came out, it had a performance of about 1. Just normalize it to 1. PC came out, it was 1, right? What was consumer demand at that time? Oh, it was at least 10. Everybody wanted at least 10 times the performance they could get. And for a long period of time, the PC was improving all the time, but demand was running way ahead of it. And we always just assumed that demand would always stay way ahead of it. And we assume that because we're the nerd community. But let's face it, not everybody's in the nerd community. And what happens is that over time, the market spreads out a little bit. The nerd community is always sitting on the leading edge. Give me all the performance I can get, give me all the memory I can get, give me the fastest this and that. But there is no necessary relationship between the fundamental improvement in the technology that underlies the system and the demand for that system or the demand for performance in that system. All right, so think about that a minute. As you get better and better at using your PC, you want a faster PC, you want more features, you want more things. But that doesn't say anything about what the rate underlying that, the improvement rate actually is. And I contend that those two things are independent and that in fact Moore's law is really what was driving the improved performance in the PC, but the demand curve was something else. Nobody really measures the demand curve, right? And the reason nobody measures it is probably partly because the nerd community is the guys doing the designs for those things, and they're always sitting at the leading edge. They never get enough of what, there's never enough for them. But in fact, someday grade school teachers start buying PCs, and they're not buying at the leading edge. In fact, we've gotten into a situation now, I think, where hardly anybody buys at the leading edge. I mean, you may still think that's the case because you're from the nerd community, but let's face it, there's a lot more population out there than the nerd community, and they're buying at Walmart. Okay, so they're buying out in the middle here somewhere. And then when they start buying out in the middle, what does that mean? That means they're buying value. They're not buying performance anymore. And when they start buying value, what happens to margins? They go to zero, right? So when margins go to zero, the manufacturers start going, hey, we got to start looking around for something that's more profitable. And so they go, hey, maybe mobile devices are more profitable, and they go over and start doing cell phones. And maybe they'll be more profitable, I don't know. But what's really important here is that it's a huge change in design objective. In the PC market, we were cost performance oriented. In the mobile device market, it's cost performance per watt. Efficiency really matters. What happened in 1971 when the microprocessor was invented? Problem solving became programming. And when problem solving became programming, efficiency went out the window. Before the invention of the microprocessor, people that designed systems cared about how many transistors they used. They cared about efficiency. They designed everything to be right down to the last transistor. The first guys designing microprocessors were like that. Every transistor mattered. But pretty soon they didn't matter. Transistors didn't matter. Transistor efficiency didn't matter. When you're writing programs, you know you're giving up efficiency because you're giving it up for productivity. And Moore's law was good enough. Remember that last chart where Moore's law is running, I think, ahead of the change in demand for performance. Moore's law kept us on this thing that said logic design really didn't matter. And so I say in 1971, at least by 1971, when we started doing programming as problem solving, innovation in logic design went into a stall. Nobody really cared about efficiency of logic design after that, except in small niches like maybe microprocessor design. But for the most part, improvements in Moore's law kept us going, kept us improving PCs and the systems that we built, in spite of the fact that we were giving up a lot of efficiency in instruction-based processing. But now that we're going we're moving from cost performance to cost performance per watt, now efficiency matters, and we have to do something about that. I gave a talk recently at a supercomputing conference, and I used this slide for them because it represents where supercomputers fit. Supercomputers are totally performance oriented. They're also totally outside the consumer market. Okay, so what does that tell you? They're probably actually inside the zero volume market for the most part. I mean, you're only selling to the government, right? But what does that tell the supercomputer guys? It says, you don't get to develop your own components. You better look at the consumer markets. You better look at the high volume markets and build your systems out of those things because you're not going to be able to do any development yourself. So this model is kind of useful for doing things like that, looking at things like that. Okay, Moore's law. I'm sure everybody here is sick to death of hearing about Moore's law. So I'm going to try an economics lesson on Moore's law instead of, here's what it actually means. What it actually means in economic terms. And the reason I think it's so great, and one reason why the semiconductor business has a growth rate that's roughly twice everybody else's growth rate, is that Moore's law works at both ends. Imagine a cost performance graph where the applications that you're trying to reach are either low cost or high cost, and there's some performance requirement that you have. Well, build a microprocessor out of today's technology, and there's some oval that fits on that graph that tells you what range of applications that microprocessor is suitable for. Anything that's below that on the cost curve, your microprocessor is too expensive to reach. Anything that's above it on the performance end, you just don't have the compute ability to get to. All right? So what happens in the next process? Two things. First of all, the cost of a transistor drops. So now if I have an electric toothbrush application and I want a $1 part and the part's $2 this year, 2 years from now it's going to be $1 for that same number of transistors. All right, so it was just unaffordable before because transistors cost too much. So one curve you're going down says I'm reaching lower and lower into the application space, and the other one says I get more transistors on a chip, or another way of looking at it is I get more performance with each generation too. So that whole bubble gets bigger in every direction. I reach higher applications every time, and I reach lower cost applications every time. So Moore's law works at both ends. So you really have sort of an economic rule that applies twice. Okay, so yield. I'm going to go over these kind of quickly because I'm sure you've seen this before, but you shrink the dimension by a factor of 2, you'd think, well, gosh, if I shrink every dimension by 2, I'll get 4 times as many chips. But in fact, you get 6 times as many chips. Because if the chips are smaller, then you can get more of them on there, more whole chips on the wafer. And the defects spread out. They don't destroy as much as a percentage of the wafer. So, interesting, you get about 6 times as many die. And this one, just a visual picture of what's happening to the transistor over time. And I put this up here for a couple of reasons. First of all, bacterium is about a micron. So, gosh, by 1991, we were already able to paint transistors on bacteria. And then by the next generation, we went through the wavelength of visible light. That meant transistors were too small to see with an optical microscope. Today, we're down in the range of 45 nanometers. We're down to virus size stuff. Wow, that's really astounding. At that kind of dimension, you can put half a million transistors on a grain of sand. To me, that's just phenomenal. Why would you ever need that many transistors? I mean, you couldn't talk to anything from, well, anyway. So that's where we are. And one of the interesting, the hot topics today are what? Nanotechnology and bioengineering, right? Well, what enabled advances in nanotechnology and bioengineering? We did, the semiconductor toads, because we're building all the equipment that gave us scanning electron microscopes and all the tools and software, everything you need to resolve molecular size features came out of the semiconductor industry. And it won't be long before we start stealing solutions from nature, right? They do all this ambient temperature processing, building seashells and things like that in environments where, we're out there doing things with 2,000 degrees and so on. They're working in seawater at whatever the temperature of the water is. So pretty soon we're going to start figuring out how they do that, and we're going to start stealing things from nature. And so I think this is a great business to be in if you're majoring in electrical or computer engineering right now, because bioinformatics is just an extension of this stuff to the dimension of molecules. Well, so wafer size getting bigger. That's a 4004 wafer sitting on a 12-inch Duo wafer. Here's the original 4004. Had about 2,000, 2,300 transistors on it. This is a photograph of it. You can actually resolve individual transistors on this thing. Amazing. And this is the march of complexity in design. I'm going to come back to why that's important in a minute. But what's interesting here is you can see this is an exponentially increasing scale. This is going from, I forget what's over here, probably, yeah, this is the 4004 with about 2,300 transistors. At this end is the Intel Duo with more than 1 billion transistors. well, gosh, that's, I mean, that looks like an exponential. It is an exponential right there, but it's also a log scale. That's an exponential curve on a log scale. Wow, that means if you put this on a linear scale, everything that was designed before about 2000 has 0 transistors on it. But the interesting thing here, the next chart is, well, sorry, the next chart is the Duo. Well, I'm not going to make any excuses for this, but the Duo's got more than 1 billion transistors on it, and those transistors cannot be resolved on a photograph. They cannot be resolved with an optical microscope because they're I think, 1/10 the dimension of visible light, the wavelength of visible light. All right, so what's happening to design cost? Well, it's following the same curve. You know, design cost probably at least doubles with each new generation. And so 2000, that's about the 4004. This is about a Pentium, 2 million transistors. And you're up here around 1 or 2 billion. Some IBM parts have more like 1.7 billion transistors on them. You know, for unit volumes in the thousands, I think. Only IBM could do that. Anyway, design cost is going up that same curve. It's just not, it's not feasible to keep doing that. And sure enough, we're not going to do that. And here's kind of the reason. This is a machine shop from probably the turn of the century. And I don't know if you can resolve that very well. The picture's not very good. And I didn't take this photo. I probably wasn't born when this machine shop was operating. And I just Googled it. And you'd be surprised if you go look for a 1900 machine shop floor photo, how difficult it is to find that looking at Google. It returns things like motorcycles. I mean, well, anyway, so I found this photo, which is interesting because this is the machine room equivalent of a central processor. You know, somewhere in the back room they got a water wheel or one big electric motor or a whole bunch of squirrels in a cage or something. And they've got shafts going overhead throughout the entire building, and everybody's machine is hooked up to that. And that's kind of what we're doing with a giant multitasking microprocessor. You know, we've got one guy in the back room trying to do everything. Well, the fractional horsepower motor completely changed the industry. It completely reorganized the machine shop. It completely reorganized manufacturing throughout the world. And so I think what we're about to see is a similar thing in microprocessors. Somebody noticed, hey, why would I walk up this uniprocessor curve doubling my design cost all the time? If I just stop at 500 million transistors, I've got probably 1/10 the design cost of that 2 billion transistor part. I just put 4 of them on the chip. My design cost is all of a sudden way back down the curve. And I mean, that's great for the part manufacturer, right? But what have I done? I've thrown a software problem over the wall to somebody else, which looks great for the guys that design the parts, but it's not so good for you if you're going to buy them and try to use them. And in fact, that's where we are we're running into trouble with that. In fact, we don't know how to do multiprocessors. Nobody has the answer to how to build a multiprocessor. And what's happening today is they go, well, you know, how complex should the processor be? You know, should it be 2,300 transistors? Should it be 1 million? Should it be 500 million? Should they all be the same? You know, maybe I should have one like this and 6 or 7 like that, like the cell processor. You know, should it be heterogeneous, homogeneous? How do I do the interconnect scheme? You know, is it hierarchical? Is it flat? Is it nearest neighbor? Do I connect everybody to everybody? So what happens is you end up with a whole bunch of people trying to build these things, and they choose one from column A and one from column B and one from column C. So right now we're running a huge experiment trying to figure out how to do multiprocessors. And we're doing, you know, what's the hardware look like for that? And the answer's not known. You know, what you see when you go, you know, I go see demos, and I'm a sucker for demos, right? But what happened? They had, you know, it's a Wizard of Oz thing. You know, somebody's built one of these weird components with one from each column, and then they've got 400 engineers in the back room doing the demo program because it's impossible to program this thing, so they just do, you know, they show you the football replays or whatever the thing's supposed to be doing, and it's really impressive. But that's because you don't see the 400 engineers that have spent 3 years trying to program this thing just to do the demo. So the demos look great, and I'm always sold on them, but then you go, well, you know, how do I do that for my problem? You know, it's great for your demo, but I'm not doing football replays, I'm doing something else. Well, here's a proof of concept that multiprocessing actually works. Here's a 300 million unit, loosely coupled multiprocessor. So we have a proof of concept that it does work. This particular multiprocessor here is 5% of the world population operating on 6.2% of the world's land mass and producing 28% of the gross world product. That's productivity. So, hey, multiprocessors do work and they scale. Here's a proof of concept for scaling. You know, now we only got 4 times the performance for you know, another 95% in population, but hey, there it is. Well, we need to work on the interconnect scheme and, you know, yeah. Well, anyway, it works. All right, so back to this thing again. Let's try to figure out where we're going to go here. Well, we don't have the multiprocessor problem solved, and I haven't really talked about FPGAs. What about them? Well, it turns out this month's Computer magazine, February 2008, here's an article, The Promise of High-Performance Reconfigurable Computing. Interesting article. I've been an advocate for reconfigurable computing for 15 years or so, and unfortunately, I'm depending on somebody else to go out and solve the problem, right? I'm just a pundit. I just say, hey, I think this is a great idea, and people don't listen to me, and but I'm not doing the work. You know, somebody's got to go out and solve the problem, and it looks like there are lots of people trying it now. So if you go read this article, there's a paragraph near the end in the conclusion section that says this. Our research revealed that they get 4 orders of magnitude in performance improvement. This is a supercomputer market they're looking at. They got 3 orders of magnitude reduction in power. And they got 2 orders of magnitude savings in size and cost. Well, that's pretty encouraging.
What problem?
Well, they're listed in there, and it's cryptanalysis, protein folding, gene, blah, 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 bioinformatics, big, highly parallel problems, integer problems. But, I mean, come on, if you can get a speed up of 12,000 times at you know, 3 orders of magnitude reduction in power, I mean, that's what we're talking about, cost, performance per watt. This is the thing that's, I mean, it's an encouraging thing. If the concluding paragraph had said this is all doo-doo or we get 2 times of this or that, maybe it wouldn't be believable. But here, at least it's saying what they measured looked very good.
And the zero volume market here, and then you build a zero volume ASIC, and you get another 20x.
No argument with you there, but hey, a lot of things start in the zero volume market, right? Well, maybe not the zero volume market, but definitely outside the consumer market. All right, so where's this FPGA thing going? You know, when I was chief scientist at Altera in 1993, and I got immersed in this stuff, and I thought, wow, this is great. You know, this is going to take over the world. And I looked back, and it didn't take over the world. And so what I did here was I took that world semiconductor market by year, and I divided it by some proxy for FPGA revenues by year. And the way I computed that proxy was I just added Xilinx and Altera together, and I said, oh, they've always had like 85% of the market, so I'll divide by 0.85. That'll give me a march of the FPGA market over time. Divide that into the world semiconductor market, and you come up with this thing. It says, gosh, they've never even gotten to 2% of the market. You know, they're not growing any faster than the real market is, you know, the rest of the market's growing. And why is that? Why is that? Well, I think there are two reasons for that. And one of the reasons is that they got the wrong customer set. You know, you look at the microprocessor market, who works on microprocessors? Programmers, not logic designers. Logic designers are the little weenies in the back room, the nerds that are designing the things. So it's the programmers that are the application engineers for those. And programmers outnumber logic designers at least 10 to 1. I've seen people say 20 to 1. So if you're limited, what if they ran out of people to sell them to? Because they're selling to logic designers. They've saturated the market, essentially. That's one possible explanation. I think another one is that FPGAs don't have good memories. You know, they're using static, you're using SRAM kind of memories. Well, gosh, if there was a non-volatile memory component that was one transistor, all of a sudden these FPGAs would jump in efficiency and capacity and performance. Everything about them would be better. But we just don't have that non-volatile memory component. Which means these things aren't very useful in mobile applications. They're not going to be good for the zero power applications. In fact, they're really not very good. Now, it turns out that I think that we're in a transition period right now. You know, Xilinx has Spartan and Vertex, and Altera has Cyclone and Stratix. And the Stratix parts are the high-end parts, and the Cyclone parts are the low-end parts. And Altera and Xilinx are both trying to manage their business very carefully so that they keep those really high margins on those $1,000 parts, but they still want the volume of the market that wants those $5 parts at the low end. Well, the real market's those low-end parts. That's where all the business is going to be in the future. And I think these high-end parts are going to be technology demonstrators. They're headed for the zero volume market. And the companies, well, they don't want to admit that yet. You know, they're trying to hang on to those high margins. They're following their customers into a corner that they won't get out of. In fact, I've told them both. Well, it doesn't matter. Those companies shouldn't be component companies. Or if they are, they need to be microcontroller companies. They need to sell to programmers, not logic designers. Well, anyway, I think, I put this up here because it tells you something about where reconfigurable computing is headed if it depends on these things, right? It's got some problems. And nobody knows how to do those either. Well, we're also running into the same thing with transistors that we ran into with the PC. We're headed for this thing I call a value transistor. The value PC was the culmination. It was what happened to the PC when its performance suddenly got to be good enough that most of the people in the market didn't need the leading edge stuff anymore. And I think transistors are in that category, or will be very soon, where they're just a commodity. You don't really need leading edge transistors. In fact, I've seen a lot of startup companies now, when I talk to them, I go, what processor are you using? They go, well, we're on a 180 nanometer. I go, hey, you don't have to be embarrassed about being 180 nanometers. I mean, Intel can be out there at 22 nanometers or whatever it wants to do. But what you care about is what do you need for your market? And I'm finding lots of companies that are just happy with 180 nanometers or 90 nanometers. So that's value transit. When the transistor came out, it was no good, right? It wasn't good for even transistor radios. They're unreliable, they don't work very well, they got no gain, they're leaky as all get out. Well, transistor improves over time. On the integrated circuit, it's improving. How's demand changing? Remember, there's probably no necessary relationship between the rate of improvement in the underlying technology and its application, the demand in the application. And I say the same thing's happening in transistors that happen in PCs. That for whatever, nobody ever measures the demand curve, right? There's just, I mean, it's just, I just drew it up there because I felt like it. But I don't know where you'd ever get, how you'd measure it. You know, what is the demand for transistors? You know, of course, all the press coverage is at the leading edge, not at the bulk of the market. And at the leading edge, yes, there are requirements. You know, there's the course. The leading edge is always out there in front of whatever progress can supply, because that's the incentive for keeping it going, or one incentive. But over time, that market's going to spread, and there are a lot of applications for which the transistors are good enough. And for those applications, they're going to drop out of investing in the leading edge. Right? As more and more of these companies start saying, hey, 90 nanometers is good enough for me, where are the customers going to come from that are supporting the 22 nanometer stuff? That customer base is going to shrink. Well, I'll summarize this. Hey, I'm going to be finished in time. I'm going to summarize this in 2 slides. What I think's happened in the market, and there are a lot of words on here, but they're for me, so I can read them. And what happened was when the computer was invented in about 1940X, and that depends on who gets to rewrite history again, right? When it was actually invented and who did it. But anyway, before that, clearly everything was fixed resources and fixed algorithms. If you built something that did something, it was all hardware. No programs in there. Invent the computer and then the microprocessor, and what happens? All of a sudden, problem solving becomes programming. Instruction-based implementations. And what did we care about? All these things plugged into the wall for the most part. We didn't have a lot of portable devices. This is like a 30-year period we're talking about here when the PC started. Solutions had to be affordable. They had to have adequate performance, but they were inefficient. Right? Their instruction-based processing is just inherently not as efficient as a custom hardware solution would be. But Moore's law keeps giving us more performance at lower cost. And if it does that at a good enough rate, then we keep duplicating those microprocessor-based systems because they're good enough to take market away from the last version. And we keep doing that until what? Until all of a sudden we have the value PC. All of a sudden the market for PCs had enough performance in it that the bulk of the market started saying, the bulk of the consumers started saying, I don't need to buy a leading edge PC, I'll take a value PC. Once that happened, the designers, the manufacturers said, I need higher margins than that, I'm going to go somewhere else. So they went through this 30-year period where nobody needed to innovate in logic design, except maybe the microprocessor designers. So we had a 30-year stall in logic innovation in logic design. And that's because nobody really cared about efficiency and power as long as Moore's law was working for us to hold that market together and keep it growing. Now all of a sudden we get to the value PC, the manufacturers start looking around going, hey, I think the cell phone's a hot thing. I can get better margins with a cell phone. I'm going to go over and do cell phones. But that changed the design objective from cost performance to cost performance per watt. Now all of a sudden efficiency matters. We went from, see, when we got the computer, we had fixed hardware, fixed resources, and variable algorithms. That gave us the huge component volumes where we had memory, which I forgot to put on the chart, had memory, microprocessors, and peripherals. Essentially 3 components. You got the whole market of applications covered. That means huge volumes and really low costs. Great. So that's fixed resources and variable algorithms. Now all of a sudden we get over here to 2003, the value PC, instruction-based processing isn't efficient enough anymore. What do we do next? Now power efficiency matters. And I think we'll go to variable resources and variable algorithms. Let's just page custom hardware in there to do the functions that we need to do. You know, if you got an iPhone and it needs to be a phone now, let's just page in the hardware that makes it a phone. If you want to play a movie on it, let's page in the hardware that makes it a movie player. And that's going to be a lot more efficient than running programs on top of some uniprocessor that's running all over the chip. So I think we'll have generic chips. That's the other thing. You can't keep building a zillion different kinds of components, because every time you build another custom component, you fragment the market. Wouldn't it be great if logic looked just like memory? And there are companies like Element CXI that want to make that happen. You know, let's just give me a cup of logic. Okay, and a cup of memory. Great. So we need a new non-volatile memory. And that's something that, now that we're trying to go to a mobile market, you know, cost performance per watt really matters. SRAM isn't going to make it anymore. I mean, if you want to do reconfigurable systems, you need an order of magnitude change in the efficiency of FPGAs. So there's going to be huge incentive to do non-volatile memory that's better than flash memory. You know, you want that holy grail thing that's got the density of DRAM, the speed of SRAM, and infinite capacity, and is non-volatile. And we're probably, you know, instruction-based processing just isn't going to do it. And I think that's That's the end of it. I've got, when I post this, I actually have 3 more slides that I'm not going to show unless somebody has a question about something, but I have 2 slides with words on them. One tells you what I think the market drivers are for this, and there are really 5 of them. There's industry transformation, which is everything's going digital now. You know, right now all the cameras are analog. I'm talking about surveillance cameras. That's all going digital. The film industry is already going digital. Everything is going digital. So you got industry transformation, ubiquitous access, mobility, modularity, and emerging economies. Those are the things that I think are going to drive us forward in the future. Those are the important, well, they're the things that are going to cause the chart that I had back there to go whatever way it goes. See if I can get back to it. Gosh, where was it? That one. You know, so, you know, they're going to be people buying a lot of washing machines. You know, we have 2 billion people that didn't have washing machines, don't have washing machines, hair dryers. You know, so there's a huge market in that, right? Emerging economies. All right, so I'm finished. Oh, and the other slide, I've got 1 slide on global warming. So, questions? Questions? Yes?
Your interesting table with all of the Intel architectures, it's not merely exponential curve, right? It's really a quadratic curve. Because what you're looking at there is the inverse square law.
It's right. On a log scale, it was an exponential curve. Right.
But it's a constant exponent, though. It's power of 2.
I don't know. So, yeah, we're through doing that though, right? Because even the last one on that curve was a duo, so they cheated, right? Made one of them and put 2 copies on there. All right, is that it? Oh, yes.
So I think you said that the future is going to lie in this reconfigurable hardware kind of stuff, right? You page in, you know, your encoder, page in your phone logic, whatever else.
Well, I didn't. Okay, question is, I said that the future was paging hardware, and no, I don't know what the future is actually, unfortunately, because, you know, one of the interesting things that's happening is that the 2 billion people that are joining the economy now used to spend 4 hours a day hauling water and manure for daily fires and cooking. And now they can be working on the multiprocessor problem, right? So they might cure cancer for all I know, but we now have, you know, people are the ultimate resource. The more people you have working on all these problems, the more problems get solved and the better everything gets. Life expectancy goes up, you know, the infant mortality rate goes down. And so I don't know the answer. I think it could be, you know, somebody will solve the multiprocessor programming problem. And so we won't get this, you know, logic that looks like memory kind of thing. Somebody else will win. I'm hoping it's reconfigurable because I've been an advocate for that, but I don't know.
So assuming it is reconfigurable, is the solution to train more logic designers, or is the solution to
Good question. So the question is, so the question is, if it's going to be reconfigurable, is the solution to that to train more logic designers? I hope the answer to that is no. Because what we need to do always is raise the level of abstraction every time we solve problems. Because productivity is General Electric used to have this thing that said progress is our most important product, and I thought that was a great motto. But now they got some sappy, stupid green motto, But in fact, the real key is productivity. Productivity is the most important product. And so I hope it's not that we want more logic designers. We don't want more logic designers. We want higher levels of abstraction. I want everything to be done in MATLAB or English. Okay, yes?
Seems like reconfigurable computing was always coming and never came, right? So
Yes. Right, it's another one of those inevitable things that never, it's always on the horizon.
yeah, and it seems like, to me it seems logical because if reconfigurable computing finds a new market, which is big enough, which is not zero volume, then somebody will come in and build a custom chip and win the competition.
So okay, I don't know if the questions show up on the tape, but the question is kind of, reconfigurable computing is kind of like Unix on the desktop. Everybody thinks it's going to be next year, and it never has been. I think the incentives are changing. And if we see a good non-volatile memory component, for example, that's going to help a lot. But the very fact that the whole market is moving from cost performance to cost performance per watt, where efficiency really matters, raises the incentive for solving the problem in a better way. And I think reconfigurable computing and probably multiprocessing, which is an analog in the fractional horsepower motor, those two things are I think the candidates for solving it. And I don't know who's going to solve it, but one of those is probably going to win. Okay? Anybody else? You guys are fatigued, huh? Oh, okay, I got. Yes.
Is there any technology besides FPGA to solve your reconfigurable?
Okay, so the question is there something other than FPGAs that might solve that reconfigurable issue? I just lumped them all together because they look similar to me, but it's probably not going to be Altera and Xilinx that solve that problem. It's going to be somebody with more incentive to, those guys are following their customers, and they'll follow them into oblivion sooner or later. So it's going to be somebody that's got a little more agility and a little more vision, probably. I mean, I shouldn't, I'll probably get emails, hate mail from those guys, but yeah, I don't think it'll be them.
I was a little surprised you mentioned reconfigurable computing as being pushed forward by need for efficiency, because one of the problems all along has been so inefficient, right?
That's, yes. So the question is,
why do you bring it up?
Right. Why are you touting reconfigurable when it's got a history of being 10 times worse than anything else?
Sometimes even worse.
I don't have a good answer for that. It's got better theoretical efficiency than instruction-based processing because it has the capability of being custom logic, but the history of implementations has been way worse, and part of the reason for that is twofold, I think, two real reasons why they've been very poor at it. One of them is those components always have completely general interfaces to the outside world, which is something that's not needed. And the second one is they've had very poor memory for the configuration memory. They essentially put an SRAM cell in the data path that's got a gate in the data path, and so they're just horrible for efficiency, and that may be an insurmountable problem. I hope not.
There's other reasons, like how long the wires are because of the way they're put together, why there's all this wire there.
Yes, yes.
Things
I mean,
of that
there's
sort that are more fundamental to the
right.
configurability and not just to the decisions that got made.
That's right. Currently, there's an issue with respect to how those chips are organized historically. Largely, they came out of the prototyping environment, the glue logic environment, PALs and GALs and PLAs and CPLDs and the whole families of those things, and they were essentially not designed to do cost performance per watt kinds of applications. And there are a bunch of companies coming along nowadays that are trying to solve those problems. I don't know if they'll really get there. It may be that, like in this high performance computing arena where they're finding 4 orders of magnitude improvement in performance and the costs are lower because of the characteristics of the problems that they're trying to solve. And so it may be that certain market wedges, they will be cost effective, but those will be things that plug into the wall. Mark?
Just a quick comments. Yes, you probably want to look at Duncan Buell's examples where you got those speed ups and lower powers.
Well,
there's a good reason for why you got those numbers. Anyway.
Oh.
At least people should look at it and they get some answers why sometimes FPGAs are.
Wait, are you saying that they're good or they're maybe not good?
They're special. The question is the metric. What is really the metric here? You can always find a metric.
Oh,
Make it look good, but that's actually a different story. No, I just very neutrally go and look at his examples. Find out why it's faster or lower power. Yes, I was surprised you could actually do certain things lower power, and I agree.
Yeah.
But
well, they're
you have
running
to look at the numbers, what they really mean.
They're also running at a 1/10 the clock speed,
Yeah,
so
but that's the good way.
Yeah.
Remember that power goes with bad with voltage and frequency. You know that. So if you slow everything down, you save something on power. Not to speak now, when you do a different task, you can again reconfigure.
Yeah.
Doesn't mean you're optimal in each segment, but overall you can be better than the competition. Anyway, these are some of the issues that. Then just for fun now, since you're talking about future technology now, like single transistor memory, you may want to look at spintronics. Although my immediate answer is that listen to the spin on spintronics. Like IBM had this big opening of their new center, and they had business charts, whatever, that was better in this, better in that, better in all the metrics. So I asked our students afterwards, so what's the real spin on spintronics? And it was very interesting. I'm not going to tell you much more.
Okay. Yes?
Why did IBM sell its hard drive business? What do they think is going to fill that?
It's not millipede. So the question is, why did IBM sell its disk drive business? I think IBM's making a transition from a hardware company to a services company. And so it's just dumping all...
Remember they started out, they were a service company. When they started, they had no hardware.
But they're going back to being a service company then, because there's more profit in it. All right, I think that's enough for everybody. So thank you.
For information on other online Stanford seminars and courses, please visit study.stanford.edu.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.